In Unit 19, we are going to look at limits of trigonometry, or trigonometric functions, and then apply those limits to some questions and differentiation. So if we look back at our sine and cosine curve, we can look at the limits of our first two functions here, sine and cosine. So if I want to find the limit as theta approaches 0 of sine theta, I can just look at the graph. So if we approach 0 from the left side or the right side, we can see that it approaches 0. So that's pretty easy to do on the graph. And we can do the same with cosine. As theta approaches 0 of cosine, as we approach from the left and we approach from the right, we can see from both sides it has a value of 1. We can also look at the limit of sine theta divided by theta using a table. So rather than use the graph, we can just sub some numbers into the table. So as we approach 0 from the left side, we'll get closer and closer and closer to 0, and then we'll approach 0 from the right side, or theta from the right side, and get closer and closer to 0, and we'll look at the values and see what result we get. So if we approach from this side, just going to fill in some values here. So you're just substituting these values into the function. And as we approach from the left, it looks like the value of the limit is getting closer and closer to 1. And let's go from the right side. We'll do the same thing. We'll pick some values that are getting progressively closer to 0 from the right side. And we'll see if we get the same result. If we get the same result as we go from the left to the right, then we know that that limit exists, and it looks like from both sides we are approaching 1. So we can say the limit as theta approaches 0 of sine theta divided by theta equals 1. We're also going to look at the limit as cosine theta minus 1 divided by theta. So same thing, we'll pick some values. We're approaching 0 from the left and the right. And let's see what we get. So it looks like as we get close to 0 from the left, we're getting close to a value of 0. Do the same thing on the right side and see if we get the same result. So it looks like as we approach from the left side and the right side, we're getting close to 0. So we can say that the limiting value as theta approaches 0 of cos theta minus 1 divided by theta is 0. So these are just some trig identities or limits that we are going to use for further questions. So we're just developing these values and looking at results. So we'll kind of summarize it together as we go through box A and B. We're sort of working through these derivatives. We'll have a summary similar to what we had in 1718, where we found the derivatives of exponential, logarithmic functions. We're doing the same with trig. We're just developing these limits so that we can use them for further applications. So in box B, you're looking at derivatives of sine and cosine. So f of x equals sine, its derivative is going to be cosine. And if f of x is cosine x, its derivative is minus sine x. So what I'm going to do is just try one of these out using first principles just to verify that this is indeed true. So we're saying if f of x is sine x, its derivative would be cosine x. Okay, so we're using first principles to prove this. So f of x plus h minus f of x over h, as the limiting value as h approaches 0. So we're doing the function sine x. So sine x plus h minus sine x over h. If you remember your compound angle formulas, there is a formula sheet at the beginning of the guide that you might want to refer to. So in 4U we had a bunch of identities that we used, and if you remember, sine x plus y equaled sine x cos y plus cos x sine y. So that's what I'm using for sine x plus h. I'm going to expand that into its compound angle formula. So it would be sine x cosine h plus cosine x sine h, and then we still have this minus sine x on the end here. Okay, so let's put the sine x in the first term here so that we could maybe factor out that sine x, which is common. So I'm going to put the sine x cosine h minus sine x together because there is a common sine x there, so I'm going to factor that out. And the reason I'm doing this is because sine x is not dependent on h approaching 0, so I'm going to separate that. So I want to find, I'm going to separate, oh, I forgot the limit there. So what we want to do is we're going to separate this first part and find the limiting value separately for these two parts. So I'm going to find the limiting value separately for cosine x sine h. So sine x, as I mentioned, is not dependent on h, so we're going to separate that and just find the limiting value as h approaches 0 of cosine h minus 1 over h. And the same in this term, cos x is not dependent on h, so we'll separate that. And just look at the limiting value as h approaches 0 of sine h. So we've got sine x, the limiting value as h approaches 0 of cosine h minus 1 over h, well, that's just going to be 0. Okay, so we'll have 0 minus 1 is negative 1 divided by 0. We'll just have 0. And then we've got cosine x. The limiting value is h approaches 0 of sine of h. Well, we already determined that in the previous example. We know that the limiting value of sine h as h approaches 0 is going to be 1. So sine x times 0 is just 0, and then cosine x times 1 is cosine x. So the limiting value of h approaching 0 by first principle results in cosine x, which we determined at the beginning. So that confirms or proves that the derivative of sine x is cosine x. There is a similar proof in the guide for cosine x. I'm not going to go through that, but you can look through that. The derivative of cosine x is minus sine x. Okay, so let's use these derivative rules to differentiate these functions here. So y equals x cosine x. Well, that is a product rule, right? We've got two functions here, x times cosine x. So y prime would be the derivative of x, which is 1, times cosine x, plus x, and the derivative of cosine x is minus sine x. So y prime will be cosine x minus x sine x. In question B, we have the quotient rule. So y prime will be derivative of x times sine x minus x. The derivative of sine x is cosine x, and that will be all over sine squared x. So let's just simplify that a little bit. So it'll be sine x minus x cosine x over sine squared x. In C, we have cosine of negative 4x. So this is a composite function, so we're going to take the derivative of cosine of negative 4x. So derivative of cosine is negative sine, and it will be minus 4x. And then we'll take the derivative of the inside, which would be negative 4. So that results in a negative times negative 4 is positive 4 sine of negative 4x. In D, we also have a composite function here. So y prime, the derivative, so the 4 stays the same. The derivative of sine is cosine, and then the inside will stay the same. And then we're going to take the derivative of the inside, which will be minus 4x. So if we tidy that up a little bit, we've got 4 times negative 4x is negative 16x, cosine of negative 2x squared minus 3. Okay, here we have sine x squared. So y prime, so the derivative of sine is cosine, so it's going to be cosine x squared times the derivative of x squared, which is 2x. Just keep in mind that derivative of cosine x squared I can write as cosine squared x. Okay, y equals cosine x squared minus 2 to the power 2. So the derivative of cosine is minus sine. X is what's in this bracket, so that stays the same. Then we're going to take the derivative of x squared minus 2 all squared. So bring down the 2. Minus 1 is power 1, then take the derivative of the inside, which is 2x. So what can we do here? We can multiply the 2 and the 2x is 4x plus the negative, so minus 4x. And then we've got an x squared minus 2, and we've got a sine x squared minus 2 all squared. Okay, down here at the bottom. So I'm going to put the power outside. It's the same thing. So now we have the chain rule. So we'll bring down the negative 2. The inside stays the same. Negative 2 minus 1 is negative 3. Then we're going to take the derivative of the inside function sine x to the power 3. So the derivative of sine x is cosine x. X to the power 3 stays the same. Then we'll take the derivative of x to the power 3, which is 3x squared. And then we'll just simplify. We can multiply the negative 2 times the 3x squared. We'll put that at the front. And then we've got a cosine x to the power 3. And we've got a sine to the negative 3 x to the power 3. Okay, in this example, I'm going to put the power 4 outside here. So now we have the chain rule. So y prime will be 4 times 3 is 12. 4 minus 1 is 3. Then we're going to take the derivative of the inside function. So derivative of sine is cosine. 2 minus x stays the same. Derivative of 2 minus x is minus 1. So let's put the negative at the front. I'm just putting it in descending order here, so by powers. So cosine 2 minus x has a power of 1, and then I'll put the sine at the end, which has a power of 3. Okay, cosine sine x. So this is not multiplication. This is a composite function. So cosine x, where the value of x is sine x. So don't mistake this for a product rule. So we'll take the derivative of cosine, which is minus sine. The inside function stays the same, and then we take the derivative of the inside, which is cosine x. So just be careful of that one. It's not a product, it's a composite function. Okay, in J, same thing. It's not a product, it's a composite function. So I'm just going to put the power 3 to the outside. So y prime will bring the 3 down. Sine x, cosine x stays the same. 3 minus 1 is 2. Then we're going to take derivative of the inside. So derivative of sine x is cosine x. Cosine x in the bracket stays the same. Then the derivative of cosine x is minus sine x. So I'll put the negative up front with the 3. I'm going to bring the 2 back here, so I'll just put sine squared cos x. And then in this bracket, what do we have here? We have cos x. Well, actually, shouldn't have a, that shouldn't be an x there. Should just be a cosine. So cosine of cosine x times minus sine x. And you could put that at the front if you want the minus sine x with the 3. Okay, so this question is quite a long one. So let's look at moving the square just to the outside. So I'm just going to put it here. So we have the chain rule. So y prime is going to be 2. And then derivative of, or just the cosine of this stays the same. Let's make that a square bracket. And then 2 minus 1 is 1. Then we have to take the derivative of the inside. So the derivative of the inside is going to be, well, cosine, the derivative of cosine is minus sine. And then this is going to stay the same. Then we want to take the derivative of 1 minus root x, 1 plus root x. So I'm going to do that separately just because it's kind of long. So I'm going to do that on a separate page. Do I have a separate page here? No, that's not what I want to do. I'm new to this share everything. Well, let's just do it in a different color. So I'm going to do it down here. So I want to take the derivative of 1 minus root x over 1 plus root x. And I'm going to, instead of doing the quotient rule, I'm going to do the product rule. So I'm going to make this a negative 1. And I'm going to change the root x to x to the 1/2. Okay, so we're going to find, so if y equals this, let's find y prime. So we're going to use the product rule. So the derivative of the first bracket is going to be, oh, I think I have a sign error here. That's supposed to be a minus. Okay, so it's going to be minus 1/2 x to the power negative 1/2. Second bracket stays the same. Plus, first bracket stays the same. Then we're going to take the derivative of 1 plus x to the 1/2 to the minus 1. So minus 1 comes down. 1 plus x to the 1/2 stays the same. Subtract 1 from negative 1 makes negative 2. Take the derivative of the inside, which would be 1/2 x to the power negative 1/2. All right. So let's see what we have here. Let's factor out a common factor. So I'm going to factor out what's common, negative 1/2 x to the negative 1/2, and I'm going to factor out 1 plus x to the power 1/2 to the negative 2. So in this first group, I took out the negative 1/2 to the x power negative 1/2. We would have one of these brackets remaining because negative 1 plus 2 is 1. So we've got one of those left. Take out a negative, so that makes that a positive. And we took out the bracket. So we took out the 1 plus x to the 1/2 to the minus 2, so we'd have one of these brackets left over. This is left over. So let's simplify this bracket. When I'm looking in this bracket, I see that x to the 1/2 and x to the, adds to 0. And then 1 plus 1 is 2. 1 plus 1 is 2. And so negative 1/2 times 2 is just negative 1. The x to the power negative 1/2 I'm going to put in the denominator. And also the bracket has a negative exponent, so I'm going to put that in the denominator. Oops. And that's power 2. So that is my derivative of the second part of this question up here. I know it's kind of confusing. So this is the derivative of this. So this goes in here. Okay. So now that we've done that, we are going to simplify this last line in the blue part. So we've got 2 negatives make a positive, so let's write this down here. So y prime is going to be 2. We've got a sine of 1 minus root x, 1 plus root x. We've got one of those. We've got a cosine of 1 minus root x, 1 plus root x. And then we've got this thing at the end here. Now, it is further simplified. You could leave it like this, but in the solutions, it is further simplified. If you remember, one of your trig identities is the double angle formula for sine x. So sine 2x equals 2 sine x cos x. So I see that here, 2 sine x cos x, where the bracket's the same. So in the solutions, if you're checking your answers, they have replaced 2 sine bracket cos bracket with sine 2x. So sine 2 times this bracket. Is it necessary? Probably not, but that's what they do in the solution, so I'm just showing you how they got that. And then this bracket stays the same. And that is the final product.